Hello again, everybody. We're going to start the next session where we will be hearing about pre-planetary nebulae and young planetary nebulae. And we start with a talk by Jose Pablo Fonfria, which is going to discuss the ionized central region of the PPM CRL 618.
Thank you. Good morning to everyone, and thanks for coming. I'm going to talk Jose Pablo Fonfria of the Instituto de Física Fundamental of CSIC in Madrid. I'm going to present our last results about the high angular resolution observations taken with ALMA of the planetary CRL 618. Okay, as you know, planetary nebulae are transient objects between the AGB phase and the EM phase. Okay, these objects are characterized for being aspherical, and this asphericity is usually associated to the presence of bipolar or multipolar outflows. These outflows they usually come with perpendicular torus-like structures made of gas and dust that are very optically thick. In the middle of these objects it's supposed to be binary or multiple stellar systems that could have hot stars. These stars could have temperatures as high as 30,000 Kelvin, and these stars are able to ionize the inner shells of the envelope, creating compact A2 regions. The gas in the outflows expands at velocities of several hundreds of kilometers per second. And we still don't know exactly how these outflows are launched. So it's supposed that maybe there are some kind of very collimated jets with the expanse at velocities of several thousands of kilometers per second that interacts with the slowly expanding AGB envelope remnant. Okay, this should happen very close to the stellar system, the stellar system. And when the stars in the stellar system are hot, this mechanism could be working inside the H2 region. Okay, this is a problem because not always we have a chance to observe this kind of objects. So, taking this in mind, Sánchez Contreras et al. Decided to take advantage of the fact that dust is optically thin in the millimeter range to observe the free continuum emission and the recognition lines coming from the H2 regions of three different stars with compact H2 regions large enough to be resolved with interferometers. So with these three stars were observed. One was a big type star called MWC M22, Young Planetary Nebula M29, and the Planetary Nebula that is CRL 618. So the first two stars have been already completely analyzed, and the results are published. So you can hear some maps for these stars, and the authors found in both rotating disks and perpendicular high-velocity jets. Okay, now it's time to do the same with CRL 618. So this star is more or less it's a PPN, more or less typical PPN, and I wanted to keep in mind two different characteristics. One of them is the inclination of the bipolar outflows here, which is more with respect to the plane of sky, that is more or less of between 25 and 35 degrees. And the second one is the presence of equatorial bipolar outflows that you can see here, that were detected for first time by Lee et al. In 2013. And these are new observations from all of that. Okay, so here you have the continuum emission of our data set. Okay, so this data we're seeing with ALMA at 1.2 millimeters with the configurations C6 and C9 to get an angular resolution of 13 milliards seconds. Well, the declination of this star is very high for ALMA, so the sensitized PSF is very elongated. And this in practice implies that the angular resolution along the north to south direction is much lower, is a factor of 3 lower. However, if you look at these maps, you can see two different continuum emission with different angular resolutions. And well, the brightness distribution is more or less an elongated distribution along the east to west direction with a complex structure inside in the center that could be described as an incomplete ring-like structure. This structure has two bright spots here, one to the north and one to the south, that dominates the emission. With these maps, we can estimate the mass loss rate to be 6 times 10 to the 6 solar masses per year. That is in good agreement with the previous estimates. Okay, if we try to, well, I didn't say, but the goal of this project was to observe the pre-grid continuum emission and the recommendation lines. Okay, if we try to get some information from the recommendation lines, the line that was observed was 830 alpha. We can see here the moment zero map, the integrated map over the frequency. That is extremely similar to the continuum emission as expected. Okay, but if we look at the moment one map, the velocity map, we see that this is a typical velocity map for a bipolar outflow that is has an inclination with respect to the plane of the sky, and with the blue shifted emission to the east here and reshifted to the west. But here there is something interesting, that is a blue reshifted contamination here that forms the distribution of this. This contamination seems to be correlated with this deficiency of emission in the moment zero map and with the southern blind spot. Okay, if we try to get some information from about the gas kinematics, we can create the position velocity diagrams that you can see here. So these are done for the east to west direction, and we define three different cuts: alpha, beta, and gamma. Here that you can see in this column and column. Okay, so the diagrams, the top diagrams are for the H30 alpha line, and the bottom diagrams are for the helium-30 alpha line, which is a weaker line that is very close to the hydrogen line and was observed simultaneously. So the first thing we can see here is that there are plenty of velocity gradients. There are many of them, but this implies that the gas is expanding with a velocity proportional to the distance. And there are two different sets of gradients that are repeated in every diagram. So this one, that is here and here as well. So this implies that it's likely that we have a kind of overall structure that surrounds the emission region. So this structure can be modeled thought to be more or less a cylinder that is inclined with respect to the plane of the sky. And yeah, we have more gradients. We have here, other gradients that are associated to emission inside this outer structure. If we look at the alpha cut, we can see that this gradient is twice as strong as those of the walls of the cylinder. And we look at to the gamma cut, we see that we have here two different gradients, one to the west and one that maybe it is a very strong very strong gradient that is not clear here. So this is because these maps are done with not too high resolution. We can get the most from the data and produce this. And this is the same, but the resolution is better. So here is much clearer that there is a gradient. And the point of this gradient, the most important thing is not the value, is the sign. The sign of this gradient is positive in contrast with the gradient that we have in the alpha, which is negative. So this has many implications, and the most important one is that it implies that there are significant differences between the expansion direction of the emitting gas in both cuts. Well, for the middle cut, there is a mixture of the alpha and gamma one. So we try to model the emission with radiation transfer code Coral. The Coral that has been used in the past with in a very successful way. And we tried many different models. Finally, we found one of them that reproduces most of the features in the observations. Okay, you can see here the model, which is more essentially a field cylinder inclined with respect to the plane of the sky, with two different objects inside that with which we try to mimic the presence of high velocity jets. Okay, and as you can see here, the inclination of these jets is a bit weird, but there is, you can see that these directions are mostly perpendicular. Okay, with this model, we can see how the structure of the central ring is very well reproduced. There is some small details that suggests that the model is not perfect, of course, and it should be even more complex. So these are the view diagrams. As you can see here, all the gradients are more or less reproduced, and well, finally we get to the most important part. So we have a very good model that reproduces mostly the emission, but we have to give it a background, a physical background to explain it. So a preferred explanation or interpretation is that these red spots are actually produced by clumps that contain stars and bipolar jets. So these stars could be part of a binary system with a Marius MEXs of between 80 and 90 astronomical units, which implies orbital periods not shorter than 200 years. The northern clamp well, the bipolar jets in the northern clamp spans around more or less along the nebular axis, but not completely, but very similarly. So this suggests that maybe precision is possible, and that maybe also this clamp or these bipolar jets are involved in the launching of the bipolar offloads that spans along the nebular axis. So of course, if we have bipolar jets, we should have accretion disks, but they are not resolved. So there are so many several questions to answer, but maybe this could be possible. For the southern clamp, we have something similar but different. So the expansion of the direction is almost perpendicular, which is something that we don't expect in a binary system. So we have to add another star. Okay. So it's possible that the southern clamp is actually a time binary system. This is something that Akasian, Shocker, and Dean Vitrum et al. In 217 and 220 used, and the last one to explain the presence of equatorial outflows in CRL 2688. Of course, this southern clamp could be responsible for the launching of the equatorial bipolar outflows that we detect in CRL 618. So, of course, this is a model. We can, when it was possible to explore the whole parameter space. So there could be other scenarios that could explain the observations. And this one works, but we cannot rule out other possibilities. So there are much work to do in order to support this model or reject it. So this is one. Thank you.
Thank you very much. Pablo, any questions for Pablo? I have a question. Have you already computed like the mathematical ages of the jets?
Yes, more or less. They range depending on what we are looking at. They can ages are years from 4 to 20. 20 years for the walls of the cylinder and 4 to 7 years for the jets. So it's they are young.
Okay. Any questions?
Hi, you mentioned that there is equatorial outflows
Yeah.
as well. Are those consistent with the ejection of a disk?
No, they are inside the disk. Yes. So it's like, sorry, what disk?
For example, the common envelope evolution, you inject a disk, right?
Yeah. No, in this case, what we have is an equatorial torus, and these outflows are inside them. So maybe what I was thinking, what we are thinking here is that maybe these outflows are launched from the southern clamp and go through the cylinder and goes out, but in the equatorial plane. So it's not possible to see them in the optical, for instance. So I don't know exactly if there is a kind of Cunebelo here, but we were not thinking on something like that. I know.
Have you heard about the weird isotope ratios? For example, in one of our papers, we found that the 12C to 13C ratio was, from our semi study, was fairly small, around, I don't know, around 10-ish in the equatorial, general equatorial region, as compared to the extended region, which is mapped earlier, which is like 13 or 14 something. So, and I think, if I'm not mistaken, we also had a fairly high abundance of the 17 isotope ratio, very close to 0. So that's telling us that something weird has happened in terms of evolution involving more than one star, obviously. So maybe it's interesting to think about connecting what you're finding here with the weird isotope ratios.
Yeah, no, it's something that we have to do still. So we have a lot of data, and this part was devoted to explain the kinematics. Just so, but now we start with the following step, which is study the lines. We have a lot of lines, so we can try to estimate STP ratios, for instance. And let's see. Hopefully, in 1 or 2 years, we will have one more paper or maybe 2 that could shed some light on this problem.
Okay, if there are no more questions, let's thank again Pablo. The next speaker is Luis Elia Prieto. And he's also going to show us some results on another beautiful pre-planetary nebula or whatever. I'm going to tell you one.
Okay, good morning, everyone. First, thanks to the organizers for giving me the opportunity to present our work. Let's start with an AI-generated nebula, just for fun. And let me tell you that we are lucky in the Bulbous Star community, because I think nature provides us with very beautiful objects that we see in the sky that probably no machine can build with. And also because they're important because the impact they have in the interstellar medium enrichment and in the growth of chemical complexity. Also, because they are fun, because most of them, I mean, from the circumstellar chemistry perspective, they are an astrochemical challenge. And in particular for this object, OH-231, it's because it's probably key in the AGB to post-AGB transition. OH-231, also known as the Calabash Nebula because of its shape, or the Roteneck Nebula because of its huge content on hydrogen sulfide, is seen in the molecular emission CO maps. low angular resolution. It's seen as a very elongated bipolar nebula, okay, with this outflow, and then let's say a central component in a short description. You can see here some of the parameters of the object. Well, it is much more intricate and complex. I won't go into the very details of the envelope because otherwise I will be here talking for 1 hour or so. So if you are interested in these details, please go to the papers by Carmen Sanchez-Contreras in 2018 and 2022. What I'm going to talk is a different angle. I don't know if it would be interesting for you. I expect yes, it's interesting, which is an observational study based on single disk data of the chemistry, of the circumstellar chemistry supported by chemical models. So this is based mainly in observation by, well, I will focus in iron 30-meter and JERES 40-meter telescopes observations, okay? Of course, we have ALMA-targeted observations. We know more about the source. And then we have also a Herschel Space Observatory spectral line survey. But as I said, I will focus on iron 30-meter telescope data and the JERES 40-meter telescope data. We detected about 500 lines of different species, about 30 molecular species, including isotopologies of carbon, silicon, sulfur, oxygen, chlorine. Among these detections, there are basic or standard traces of circumstellar chemistry of oxygen-rich objects. And then we detected very interesting emission of nitrogen-bearing ions that were not seen previously in oxygen-rich objects. So we did a very standard analysis of the source, like feeding the lines, analyzing the molecular emission from the velocity components in the spectra, and then since we have a very broad coverage in the spectral range, we were able to detect many lines covering a huge range in energy for different lines of different species. So we were able to carry out population diagrams like the one seen here for carbon sulfide, and then also LTE and non-LTE modeling to extract some of the most important parameters of the envelope, and namely for the chemistry. I won't go very much into detail of the rotational temperatures and so on, but the chemistry, and here is a bar chart of the abundances of the molecules detected with these studies. From the most abundant, which is of course CO, to the less abundant, the carbon sulfide with the substitution of the 33 isotope of sulfur. Those you see with the red asterisk is strictly have to be taken as lower limits because of opacity effects in the lines probably. But if you take a look in the chemistry, you will see huge content, enhanced content of sulfur-bearing molecules and nitrogen-bearing molecules, which is rarely seen in AGB standard envelopes. So for the chemistry, what we did is we used the tools that we have at hand, and that includes chemical equilibrium models, which in fact are not very useful for this type of source because it's more suited to AGB standard envelopes, around these envelopes and to the innermost region of these envelopes where you have high densities. But instead we use chemical kinetics, gas-based chemical kinetics. And we branched this into two different models. One is model A, which tries to mimic the central component, like a remnant of an AGB circumstellar envelope, although we know that this has been disrupted and there is more complex environment inside. And then model B, which is trying to mimic the outflow, the wall of the outflow of this, of the bipolar outflow of the source. Applied to the nitrogen-bearing molecules, it is disappointing from the chemical perspective that you don't reproduce the observed abundances. In general, for the most fancy molecules, HNCO or HC3N, except for nitric oxide, which in principle is well reproduced by the models. Here you can see, well, this is, if you see abundance relative to molecular hydrogen versus distance, you're seeing results from model A. If you're seeing against the time, you're seeing model B, so the model of the wall of the outflow. And then for nitric oxide, as I was saying, this one is well reproduced probably in the outer parts of AGB CSE, and this is because the reaction between photodissociation products of molecular nitrogen and OH as a main product of photodissociation of water. but the other ones are not well reproduced by several orders of magnitude. So what we try to do is to sophisticate the models, put in some extra ingredients like nitrogen enhancement that could be caused by hot bottom burning. This was applied to putting more nitrogen in the thermochemical equilibrium models, processing that, and then put the results into the chemical kinetics. But let me tell you, this one doesn't work at all. I mean, it doesn't reproduce the abundances of these fancy nitrogen-bearing molecules. And we had an also additional problem, since nitric oxide was already well reproduced by chemical kinetics. Then if you put extra nitrogen, you will unrealistically overestimate the abundance of NO, so it's not working at all. And then we tried an additional ingredient, which is put in the companion there, that would produce extra UV ionization, causing for the dissociation of more molecules and maybe producing a more rich environment, but it has a negligible effect in the abundances predicted by our models. And let me know that at this point, I'm citing here most recent papers, but there are also several authors that mention that there could have been a merger in this object. So that could be something that has to be explored in terms of different elements enrichment, not by intrinsic processes like hot bottom burning, but extrinsic processes. And also we detected several ions, interesting from the chemical perspective, that were usually not abundant in more standard oxygen-rich objects like HCO+, N2H+, H3O+, or SO+. The models, again, for these models, what we played is we tweaked another parameter, which is the input abundance of water. This is a parent molecule in oxygen-rich envelopes, and in principle, it will change your results because it either works as a formation agent of, it reacts with some of the molecules, enhancing the products, or either is a molecule that will lead to the destruction of other, activating other paths that will destroy your molecules. Like, for example, for N2H+, if you reduce the abundance of water in your models, you will see an enhanced emission of N2H+ in the inner envelope because of this reaction. But again, a decrease, playing with the water produces maybe compatible abundances for SO+, but not for the rest of molecules. Not only, sorry, I forgot to mention that these are the observed values. If you see in the right side of the chart, that these symbols, they represent the observed abundances. For SO+, they could reproduce the observed abundances. For the rest, it's okay, but the problem is also that there is a ratio between what we see analyzing the different velocity components, the emission from the central component and the outflow. The ratios doesn't match. So the chemical kinetic models, they are also not reproducing the rest of the abundances. And let me here note also an important mechanism related to these cations and ions in general, which is cosmic ray ionization and photoionization in general. And HCO+ could be a tracer of soft X-rays. And you can see, well, later today, the talk by Jaime Alonso that will talk about this nice effect that can be used to, trace the nature of these objects. And then about the detection of methanol. Well, methanol is a molecule that has been detected in molecular clouds. Thanks. In molecular clouds and also strongly irradiated PDR regions. In principle, is a very complex molecule that is difficult to form in gas phase. And that is because you need to activate some reactions that have energy barriers. And then you need a very high density or temperature in the gas to enhance these only gas phase reactions. But there is another path which is also more common in these clouds because they have, in the grains, they have ices. We know the conditions are not the same in the evolved stars, but I think it's something also to be explored. In this case, the presence of sharks could extract some material from the dust grains or from the ices to the gas phase, and then provide more elements for the reactions and produce this methanol. But in any case, we played with our chemical kinetic models, again, gas phase only, trying to put some more energy to the gas. And let me tell you, it's impossible with realistic conditions to get abundances predicted abundances, methanol is the red line, that are compatible with the abundance observed from ALMA observations. So, comparing with other sources, I don't know if Ticum chemistry could be used. I mean, I think there are several things that can be used as a test for the stellar stage, I mean, the evolution stage of the object. When we compare this object to other similar objects, I mean, evolved stars, for example, with carbon-rich objects, we know that carbon chemistry is in general more active than oxygen, so the diversity in carbon-rich objects should be, should be more diverse, chemically speaking, type of objects. But in fact, this falls for the comparison against IRC 10 to 16, but that probably is an observational bias. And the situation has improved in recent years, as Ramlal showed us a couple of days ago. The number of observations, I mean, general chemical studies of carbon-rich objects has improved. And then we see that always 231 is doing well. I mean, it's quite diverse and rich compared to these objects in numbers of 30 detected species or so. When you compare it to a more standard oxygen-rich object like Aikita, we had a similar 30-meter survey. And the difference observed in terms of content is that we observe in OH 231 signs of shock-induced emission. And it seems that OH 231 appears to be poorer in molecules that are typically found in the inner envelope. Compared against a more massive star, Guillermo Quintana-Lacasi, which is in the Argons, also with a 30-meter partial survey of the source. And again, we find signs of shock-induced chemistry more active in OH 231. It's probably poorer in nitrogen-bearing species. That's something that has to do probably with the mass of the star. And I mean, a different evolutionary state. And then we have comparison with some peculiar objects. Mark Seaver showed also a couple of days ago this nice object is remarkably similar in chemical content with OH 231, and particularly one that I love is 1157, a young stellar object, which in fact displays emission from OECS, HNCO, like in OH 231. The difference here, the difference between the two, or not difference, I mean, we have here some shock processing of dust and ices. And also we can mention, for example, CK-Wu. We also saw that in a couple of days ago. And just to wrap up, these are my conclusions. Now we're working to try to constrain better the shock chemistry with deeper observations. We have further observations, developing more sophisticated chemical models, probably including hydro and some kind of machine learning methods. Probably it would be good to do some JWST observations. Difficult for this source, probably, and trying to do an accurate determination of isotopic ratios for the better characterization of the nature of the subject. That's all. Thanks. Sorry for the 30 extra seconds. Thanks to the audience.
Thank you, Luis. Questions?
First of all, I applaud Carmen's new classification, the new class, the whatever class. So, I mean, you seem awfully calm about the subject. So the fact that there's an AGB, there's a Myra inside, and there's quite a lot of mass in the nebula.
Well, yeah.
Meaning that some has come out, but he's still an AGB star. There was an ejection. So is there any, am I missing something? Is there any resolution as to the fact that this doesn't make a great deal of sense?
I don't know how to answer that question. I mean, I think most of us see some peculiar objects. I mean, we're missing something, but this object is as it is. I mean, from the star is what it is. I cannot tell you why, but I mean, probably the fact that is within this violent episode of mass loss is that we. Well, similar in terms, I mean, it's an AGV, but the mass loss rate, I mean, recent mass loss rate was determined by Javier Arcolea, and it's close to 10 to the -4 solar masses per year. Akita is much less. I mean, it's 2 orders of magnitude. Well, not 2 orders. It's 5 times 10 to the minus 6 solar masses per year. But also, there's probably an observational bias in the characterization of circumstellar chemistry because the 30-meter telescope observations of both sources took like 150 hours per source. I don't think any other sources, except for what has been doing, or Ramlan, or other people has been doing in terms of circumstellar chemistry. I mean, there's a lot to do, but it's difficult to progress because you need too much time. I mean, too long time to integrate, and you don't get favorable reports from evaluators in ALMA, for example, when you try to find molecules.
Just a comment in response to what Ursula just said. So counterparts, this is oxygen rich, there's a carbon rich star behind her, which also shows
Yes.
beautiful collimated outflows,
Yes.
parabolic outflows, and then there's an S star, Pylon Crew, which also shows similar structures. So they are these, I don't know, you call them unique or weird or whatever, stars, which are still AGB stars, but they're showing all the evidence of the very fast outflows, equatorially dense structures which you see in pre-planetary nebulae. So yeah, you have to try to
Yeah.
understand.
That's true. Yeah, I mean, V Hydra is a very good example in the other side, the chemistry.
Can I add something to this? The most recent work we did on this subject, trying to understand what the central source is, actually revealed that now it is, it has the A-type companion. I mean, the AGB star can be transferring, the mass through Windrow's low overflow. Well, all the parameters seem to fit well in the MLAS model, for example. So that is a possibility now. And actually, what I wonder is why we cannot find more objects like this, because there must be a lot of AGB stars with, companions that are not, relatively close, doing this kind of stuff. So I think that's also the question probably we have to think about.
Mm.
But there's another question. Do we have time for?
I mean, I think one reason we don't see more of these companions is that they're contributing to the dust formation. Why you have the dust.
Could be.
Yeah, similar to what I was showing for high group. Makes it harder to see them. A star is pretty bright.
Yeah, could be.
Thank you very much. We move on. Thank you. We move on to the next talk by Elisa Massa. Yet again, a beautiful planetary nebula and 132.
Hi everyone, I'm Elisa. I'm a PhD student at the OAM here in Madrid. And today I'm going to share with you one of the main projects of my thesis, which is a morphokinematical modeling of M192, a preplanetary nebula that I'm sure some of you are already familiar with. So I hope at the end of this talk I can give you a general view of the nebula and what it tells us about the end of its central star. So first of all, let's get to know the nebula. M192 is also called Minkowski footprint because of how it looks in the optical. It is a bipolar nebula located 2.5 kiloparsecs away. It has a kinematical age of 1200 years, expanding with a Hubble-Eigelstig gradient, and one of its most iconic features is that it has two not so ionized gas inside the lobes here that add around half the age of the Rostov nebula. It is one of the richest nebulae in terms of molecular content, and it shows characteristics of both C-rich and O-rich environments. We made our model using Shape, which already introduced Miguel earlier this morning. Shape is a 3D modeling tool that, together with ShapeMold, performs the radiative transfer of molecular lines. And as Miguel mentioned, as part of this project, I computed the tables to enable the shape and shape mold and to use the new molecular species. So if you're interested in this kind of modeling, stay tuned because they will be public as soon as my last paper that is already under reviews is published. Here, as an example of this modeling process, I put some intermediate versions of the model. Here is one of the previous I made that select some of the structures, and here the are pretty good one enough to be shared last year. One of the most important features that we needed to determine about the nebula before starting modeling was the inclination of the nebula with respect to the plane of the sky. For this, we just made the assumption that the walls of the lobes for the nebula are have a fixed radial velocity gradient, and that the nebula has a revolution symmetry. With this, just making different cuts at different angles, we will get the right angle the moment we get the revolution symmetry, which for us was the 40 degrees when we get a full circle. So this is the final model. Our model is made of 6 different structures. The main shell that is divided in the equatorial area of the ring, central cylinder that goes inside the center of the nebula and gives the shape of the base of the lobes. The spheres, which play the role of the nodes with ionized gas that are put inside the shell, and the tips at each end of the nebula that have a double layer structure with an outer part and an inner part. These structures are filled with the physical properties of temperature, density, velocity, flow, and turbulence. Important to mention that we find a front-like velocity law for this ionized gas in the nodes, but overall we can differentiate 3 types of bigger structures: an outer layer that is composed by the shell, the ring, and the outer tips, that is made of cold and dense gas. The inner material that is composed by the spheres and the inner tips, that is way less dense, warmer and more turbulent. And then we have the transitional structure that is the central cylinder from the core of the nebula to the outer cold layer. After several iterations of fitting the data, we are finally able to get a value for the abundance of our observational data. We used 5 interferometric maps and 23 single dish lines, all fitted in by our model, of 3 different molecules, which are CO, HCO+, and HCN, and their different isotopologues here listed. Our fitting process to get to these final abundance values, we're basically taking the observational data, which we see here in a PV diagram, performing the reproduction by our model, and seeing the residuals by subtracting the model from the observational data. And with these values, we can compute isotopic ratios, which we can see here. We see the most shocking part for us was finding that we got different isotopic ratio values for 12-13C, depending on whether we use CO or HCO+. And which were also compatible with HCN. Here in blue, we fitted the model for a ratio of 30, and in pink, a ratio of 10. And we see they are totally incompatible with in seeing if we use the CO lines or the HCO plus lines. So in the end, we conclude that we were tracing isotopic ratios by ages because the HCO plus was tracing the inner parts that were the inner structures that were only around the main axis, whether CO is tracing the more outer, colder part of the nebula. But the main point I want you to take is that our model is the best way of analyzing this kind of nebula in depth, because when we produce a grid with all the physical values of each point of our model, so we are able to compute all the values for like total kinetic energy, linear momentum, the total mass, and we also can play with these results to be able to see what's the contribution of each part of the nebula. Here, as a curiosity, I also computed the radiation pressure age to highlight that the momentum axis is found only on the outer part of the nebula, but not in the later ejected blobs, let's say, around the main axis. As I said, we can play with these results as much as we want. We can also plot them in by latitude of the nebula from 0 to 90 degrees and see the contribution of each part of it, which I think this helps a lot in defining the models that give the results to this kind of nebula. And we can mostly map the final values of the physical properties of the nebulae. Here we have the density, temperature, kinetic energy, and linear momentum by each part of the nebulae. So the main point is that with this method, we can get a very detailed view of each of these values thanks to the 3D modeling. It is true that our model is not perfect, especially we're very limited by the NUIMA resolution, which gives us some inconsistencies, especially in the central area. Here, if you notice it a few slides ago, there is a central bright spot that we are unable to model due to this lack of resolution. But overall, we are able to impose strong constraints to our shaping process, and we can get an overall view of how this nebula was formed, which it all indicates a common envelope ejection. So how do we conclude that there was a common envelope ejection? Basically, we have a very massive nebula of 0.8 solar masses. The isotopic ratios of 1780 indicates that the initial mass of the central star was around 1.7 solar masses, for which 0.8 solar masses of the nebula all ejected at once would have been enough to interrupt an AGB phase in there. And this makes it chemistry that we find in the molecular content of the nebula also indicates that despite the central star being destined to become C-rich due to its initial mass, an interruption really fit that mixed chemistry that we find with both O-rich and C-rich characteristics. Also, this jungle rejection around the main axis tends to be an indication from binarity, and the different 12-13C isotopic ratios that we find, despite being quite shocking that in the isotopic ratio changes with age. It seems to be not as weird for experts in nucleosynthesis, and they agree that this will fit with a central star of between 1.5 and 2 solar masses. So yeah, we still have some open questions. We don't know exactly, and we can access the very center of the nebula. But overall, we give a full study and the full view of how this nebula was formed from the central star death to the from the final view that we see nowadays. So as a last point, just representing that we are trying to search for more in other nebulae. We have a project for in ALMA and NOEMA trying to find this change in isotopic ratio. So stay tuned for more. Thank you.
Thank you very much, Lisa. Questions?
Very nice work. I'm wondering if you had a chance to compare with our modeling of this nebula using the HST images where we modeled the scattering light. And so we got an idea of the dust, and then using gas to dust ratio, we derived the total mass of material, right? We had a somewhat similar geometrical structure with a fat torus, bipolar lobes, and these little blobs in the middle. Most of the mass is in this fat torus, and the gas to dust ratio of 200, we derive total mass of about 1 solar masses. And of course, the gas to dust ratio creates an uncertainty, but the fact is larger than what you have may be real because the CO which you detect is going to be photonic dissociated at some radius, whereas the dust is tracing everything which is there. So, but I mean, the fact that we have a lot of mass ejected in a short time is clear.
Yes.
Yeah, pointing to C evolution. Yeah.
There was several questions, I think, some.
Thank you very much for a very clear presentation. I don't have so much a question because what you said is very clear, but I have a recommendation. Would you and all the other people who make these models please also consider plotting the Mach number? You have enough details to do that. Just the ratio, you could have temperatures, you do the ratio of the local speed of sound and the local flow speed. The reason that that is important is that the Mach number is dimensionless, and therefore it is much more robust when assessing how good these models are.
Thank you.
Actually, my question is similar to Sahai's. Just to make sure I understand your model correctly, the optical light are all due to scatter light. So they are scattered off the molecular walls surrounding or from the torus. I mean, where are exactly the relationship between the molecular gas and the optical nebulae?
I put the optical. This one.
Yeah.
The light that we see here is the reflection of the ionized gas inside the walls of the lobes. So my
Please
model,
analyze, yes, yes.
yeah. So my model is like tracing this part here, and the ionized knots is these spheres that we find in here, or at least they seem to match with the optical data of in other ionized of that ionized gas. And here we give it here. The ionized gas that we're seeing in the optical, it matched our first year that we reproduce with a front-like velocity distribution. So yeah, we believe that that's how our model, it goes around the lobes in the outer part, and the ionized nodes match the population of our spheres here that we see in HCO plus and ECM.
Sort of government sense.
I had a question about your 12C, 13C isotopic ratio. So you see a difference between the CO and the other molecules. Do you have any other molecules that would give you the same spatial tracer as CO so that you can actually avoid being affected by differential photodissociation between CO, well, between the 12CO and the 13CO, whereas the others do not get affected by that?
Not actually, not at this with this data. We tried to put an ALMA proposal to make something like that, but hasn't been successful so far. So yeah, we are trying.
Okay, thank you. Save your questions for the discussion, please, and thank you. And the last talk